Hello, everyone. So today we're going to be diving a little bit into the ideas of conduction. So again, the major idea when dealing with conduction is that I'm going to need to make use of a hot substance and a cold substance. So this is essentially going to be trying to take a hot material and a cold material and putting them in contact. So, for example, classic one is I may have a chemical stream that I need to warm up, and the typical approach is I'm going to use hot steam. Um, and then something that's nice and conducting, like, say, a metal pipe, to allow the transfer of heat in between the two parts. So, an energy balance is going to tell you kind of how much heat needs to be transferred, though it's not going to really tell me about exactly how I can transfer the heat. So, it may neglect things like what sort of apparatus or material may I need? What sort of area may I need for the contact in between my hot material and my cold material? A lot of this information is all kind of embedded in the heat transfer. So in order to determine this, we're going to need to, first of all, know our contact area. So how much contact do I have between my hot and cold material? I'm also going to need to know the identity of my conducting material because, for example, as we know, metal is a much better conducting material than, say, something like brick. So we're going to need to investigate a little bit more into this. And it also makes sense that this will largely be driven by the temperature difference in between our hot and cold material. The greater the temperature difference, the more the heat tends to flow unidirectionally instead of in a bidirectional fashion. Or in other words, this helps encourage a faster transfer of heat. So again, the first thing we're going to be doing, because we're mostly focusing in on big picture, is we're going to be looking at steady state conditions. So we're going to assume that our heat transfer is going to have a single value and it's reached, well, a steady state. So in order to approach this, our go-to equation is going to be Fourier's law. So this is essentially going to develop what's called a heat flux. So this is going to be the amount of heat transferred per area per time. The traditional units are going to be joules per meter squared per second. However, watch out as some people will start fooling around with these units. For example, we may have per centimeter squared, and the time point may be something like per hour. But if you don't see otherwise, tend to assume these units. This is going to be driven by the actual rate of the heat transfer. So this is my size extensive heat transfer rate, which is going to typically be in joules per second, and is going to be mediated by our contact area. So I'm going to have a large heat flux when I have a large amount of heat transferred over a fairly small area. Now this is going to now we're mostly going to be looking at this heat transfer in a one-dimensional sort of perspective. You can develop this into a multi-dimensional model, but it's often done by looking at each dimension individually. So this is actually a pretty good place to start. So we're going to be typically describing everything in the direction of heat flow, with our direction of heat flow being in the x direction, and the larger the x value, the greater the distance the heat has to travel, which is going to be specified specifically as dx or delta x in a non-infinitesimal fashion. Similarly, what we're really going to be looking at is how much the temperature, our dt, is going to change for any given distance. So we're looking at essentially how quickly temperature changes per distance of time. So you can also imagine this as watching the temperature slowly get cooler as I cross the conducting material. So I start out hot as I'm in equilibrium with my heat source, and end cold as I'll be equilibrium with my cold material, and then a slow drop off throughout. However, this is going to end up largely the ratio of temperature difference to distance into the material is going to largely be related to the heat transfer via our thermal conductivity. So this is essentially going to be a property that describes how well my material conducts energy. And this is either going to be given as watts per meter Kelvin or joules per meter Kelvin per second. So again, watts being joules per second, these two units are going to be synonymous, and I'll move between the two rather loosely. So watch out for that. So let's go ahead and look more at this last property. This is going to be a large control in our heat transfer because we should be able to measure the temperature of our hot and cold material, and we should be able to measure the thickness of our material. So this is going to be the real big thing that's going to control heat transfer. So again, our thermal conductivity is going to be a measure of how well heat transfers through a substance. And so to give you some ballpark ideas of what these values can typically be, for gases, these are going to be fairly low. So for something that's non-reactive like CO2, closer to 0.01 up to about, say, 0.1 for methane. They may get a little bit higher, but traditionally, most gases, fairly low Ks, which result in fairly low heat transfers because there isn't much material to transfer that heat, especially in a conductive form. Conversely, for liquids, they'll tend to have much higher conductivities because the material is much more densely packed, so there's a lot more collisions taking place to transfer this heat. And so that these typically are in the range of about 0.1 to 1. Water's kind of fairly typical in the middle at about 0.5 watts per meter Kelvin. Now solids are our good solid conductive materials. So they typically go somewhere between about 0.1 for a non-conducting material like brick, which has a lot of internal air spaces to help slow down heat transfer, all the way up to, say, something like 300 watts per meter Kelvin for something like copper. And one of the things you really should watch out for is that some materials may actually have multiple K values. So a good example of this is actually wood, because it turns out that you have long strain fibers going with the grain of the wood, making it a fairly conductive material. Conversely, if I'm trying to cross the grain, I run into barriers of water and air as I have to go in between the wood fibers. So for example, if we look at pine, it turns out that the heat transfer coefficient is over twice as large if I'm going with the grain as across. So if you want to make sure that you're building if you're using wood to build a insulating material, try to make sure that you align so the heat has to go across the grain instead of with the grain to get the most out of your to get the most insulation out of your buck. So now let's go ahead. However, if you want an example of more K values, feel free to take a look on Blackboard, where I've put together several tables of coefficients for you to kind of get an idea of typical heat transfer coefficients and how choice of material can greatly affect these heat transfers. So let's go ahead and assume I have that I have a system composed of a single material as an insulator. So I want to figure out how fast heat transfers through a copper pipe or through a brick wall. So in this case, it's actually fairly straightforward, as my heat flux is going to be related by Fourier's law to my coefficient times the difference of my temperature. So typically it's going to be expressed as negative of the inside minus the outside, all divided by the thickness of the material, which we're going to represent as B. So let's go ahead and work a real problem to kind of see how this all comes together. So let's look at a nice classic insulating material, fiberboard, classic construction material. You may even end up using this as an insulator around a reactor, as it's fairly cheap and not a bad insulating material. So let's try and calculate the heat flux through a 25.44 millimeter insulating fiberboard, which is a typical thickness, where we're going from from an inside temperature, say a warm system of around 250 2.7 Kelvin. So this is about 75 degrees, 70 degrees Celsius, and an outside temperature at about room temp. So I'm going from an inside heated box to an outside typical temperature. So in order to go ahead and solve this problem, I'm just going to need to simply put it through Fourier's law. So in this case, we have our inside, outside, convert our distance into meters, and then we have a coefficient of about 0.048 watts per meter squared. So this is sitting on a more insulating side of a solid material. So what this ends up translating to is that fiberboard under these temperature regimes should allow about 100 joules of energy to flow through per second uh, through every square meter of fiberboard. So this is actually a fairly insulating system and will have relatively low heat flows. But again, when you start scaling this up on a per second basis up to, say, minutes or hours, this is actually a fairly substantial heat loss, and you may want to choose better insulating materials. However, one of the things to watch out for is while looking at the insulation through a plain sheet of material can actually be fairly useful. One of the things we have to watch out in industrial chemistry is that most of what we're looking at is going to be through pipes. So what I'm going to try and do is figure out how heat transfers from inside a pipe, where I may be pumping chemicals, to the outside atmosphere. So I may have a cooling liquid out here, or I may just have plain air. At this point, we're mostly looking about how the heat moves through the pipe itself. So it turns out we can actually use Fourier's law for this as well, as again, all it depends on is the thickness of the material, the temperature inside, and the temperature outside. So we can get our flux fairly easily. But what becomes a little bit trickier is trying to go from our heat flux, which is in a per area basis, to our actual heat flows, because this is going to depend upon the area of contact. And this is where pipes are a little bit difficult, because pipes have a smaller area inside than they do outside. So which area do you use? So there's already a hint here, because I put a subscript on this area. Turns out we're going to make use of something called the logarithmic mean of the area, which is essentially a fancier version of taking the average. So the idea of the logarithmic mean is I'm going to take the difference of the outside and the inside area and then divide it by the natural log of the ratios of these two areas. It's essentially a more accurate version of taking an average. So it turns out we can make use of some basic trigonometric properties based on the fact that that the area is going to be the same as 2 pi r, the radius, or the same thing as pi, the diameter of the circle, times the length. Well, the inside and the outside are going to share the same length, and they're going to share pi. So I can move pi and the length outside, and then all I'm left with is a ratio of the two diameters. So we can express the logarithmic mean as pi times the outer diameter minus the inner diameter divided by the natural log of the ratio. And don't forget to factor out the length of the pipe. So this gives us a nice abbreviated equation to work with. Now, let's try and work an example problem, because this is kind of a lot of information to work with. So let's say I'm going to try and cool a system by feeding this the solution through an ice I'm going to try to cool a solution by feeding a ice solution through a hard rubber tube uh, with an inner diameter of 5 millimeters and an outside diameter of 20 millimeters. So essentially what I have is a cooling tube running through a reaction bath that's about 25 degrees warmer. So now the real question is going to be, how long of a tube is going to be required to remove, say, 14.65 watts of energy? So again, this is going we can imagine this energy value coming from essentially how much energy the reaction is producing per second. So in other words, I'm going to need to remove this amount of energy to keep the reaction from running away on me and heating up too much. So in order to solve this problem, I'm going to need to know the heat transfer coefficient of rubber, which I have right here. Fairly insulating, but you may notice not quite as insulating as something like fiberboard, which can be a little surprising. So in order to go ahead and solve this problem, let's go ahead and write down essentially what we know. I know the inner diameter is about 5 millimeters. The outer diameter is about 0.02 meters. Have my coefficient of rubber. I know the heat value, and I know what the inside inside and outside temperatures as well as the thickness are, simply by doing the difference in the diameters. So when we end up expressing this, we have our classic form of here's my coefficient, difference in temperature, and the thickness of the material. And what I've essentially done here is I multiplied my flux, which is this term, times my area. So when we do this, we can go ahead and plug in our equations and try and rearrange it to solve for L. So again, L is going to be related to the actual heat transfer divided by all the other parameters. The rest is a long series of plug and chug. Feel free to walk through this to make sure you're comfortable with the equations. But what we end up coming up with is I need about a 0.96 meter rubber tube of my ice solution essentially flowing through to maintain this constant heat transfer rate. So from here, you can essentially use mass balance and energy balance to figure out what rate you need to send the material through this pipe to essentially ensure a constant temperature and thus this constant temperature rate. So we'll get a little bit more into that later, but next time we're going to deal with a little bit more simpler set of problems, which is the fact that it turns out most of the time my walls aren't composed of a single material. So next time we'll deal with heat transfer through composite materials. Till then, take care.